for Market Graveyard.
Put your garbage can up there.
Oh, I didn't notice that. There's a recycling bin up here. Oh, yeah. What? Yeah, but I've seen students toss a lot of things in the recycling bins around here that are definitely not recyclable. What? All right. Okay. Whatever. This laptop is smaller than the other one. Do I still need to?
Probably not. You're good. You're good, actually.
Draw logs.
You actually got about a 2-inch clearance, so you're good.
Okay.
You're good. So just don't write down to the metal.
Okay. Fine. Okay. So one thing I need to recap in conjugate gradient, or CG, we have each of these vectors, these QJs, is some polynomial of A multiplied with B. And these polynomials, these are orthogonal, really orthonormal polynomials with respect to a specialized inner product. And that inner product is of two functions f and g is B transpose f of A, G of A times B. Assuming f and g are real, otherwise they would take the complex conjugate of f. Now, here's where our first complication comes about. Is that this is not a valid inner product if A is not symmetric, positive, definite. Okay. Because one important property to be a valid inner product is that if you take inner product of a function of itself, that would be the norm. It has to have all properties to be expected of the norm. But if A is not symmetric, positive, definite, we could have, for instance, negative norms of functions. So, so that's out. Now, what is the consequence of this is there is no short-term recurrence relation for these vectors, these Q's. Whereas in conjugate gradient, or really it was Lanczos, we had this three-term recurrence relation. Each vector could be expressed in terms of the previous two. So, so we've lost that. So it's at this point where we need to do things a little differently, because we still want these Q's to be orthonormal. So we want to preserve the fact that these vectors are orthonormal. Instead of using Lanczos, what can we use to take a set of vectors and make them orthonormal? Gram-Schmidt. Yeah. So Gram-Schmidt orthogonalization. Okay. So I'll go ahead and describe that. Of course, now I'm having flashback to my very first linear algebra class where we had to perform Gram-Schmidt on given sets of vectors. And of course, my classmates and I had to pronounce Schmidt a little bit differently. All right. So Now, it turns out actually Graham-Schmidt is the third and not as effective way of computing the QR factorization, because the QR factorization is a way to take a given set of vectors, columns of A, and construct a set of orthonormal vectors from them, the columns of Q. And the coefficients involved in doing that are the entries of R. So I'll explain that when I describe the Graham-Schmidt algorithm, which fortunately is not very complex. Oh, this chord is... Okay. For the algorithm, at least how we're going to use Graham-Schmidt in this case. Well, actually, yeah, I have time. I'll give a general algorithm and then describe how we're going to use it for iterative methods. Now, Graham-Schmidt generates the thin or economy-size QR factorization. So A is m by n, Q is m by n also, and R is n by n, and over triangular. That's not very good over triangular. That's not much better, but it'll do. I did the exact same thing, didn't I?
Looks like an equilateral triangle. A little bit.
Well,
You can just take a third try. I mean,
no. Yeah.
I
Well,
mean,
a upper triangle should be isosceles, I guess, for a square matrix.
Right.
So, okay. I'm not going to do a third try because I'm also not very tall, and I'm just going to screw it up. So,
it was the dumbest comment ever. I'm sorry.
it's not.
No, I'm talking about him telling me to write higher on the board.
Oh, that. Okay. Yeah. Yes, that was dumb.
Oh.
You already met with her? Wait, you already met with her? You know what's going on, never mind.
Yeah, I need to meet with you about that.
Always last everything.
Dr. Schroeder told me I need to use the top of the board. I can't reach the top of the board.
He's not very tall either.
I could hardly erase it after you used it.
I hope he never watches this.
You're not very tall either.
Oh, we're on YouTube right now.
Yeah, we're on YouTube. I don't care. I don't care.
Okay. Yeah. Anyhow,
It makes these videos more fun. I forgot what I was writing. Ugh.
all right. So our matrix A has these n columns that are not orthogonal or orthonormal or anything like that. So what we do is, so first I set R1 to be just A1, and then Q1 will be R1 over its 2 norm. So it's normalized. The Q1 is the unit vector. Then R2 is going to be A2, but I need to make sure, I need to orthogonalize A2 against Q1. So what I do is I subtract off Q1 transpose A2. So that's just a dot product there. Keep in mind, I get into trouble every time I give this lecture. Try to distinguish my A's and my Q's. The Q's have the nice long tails. And if I need to, I will exaggerate them. And then, now I have R2, I will normalize that. Okay. and this process continues. So the thing is, as I go from one vector to the next, I have to subtract off more and more terms. So I'm orthogonalizing against everything. So for example, R3 is A3, and now I got to subtract off two terms. Q1 transpose A3, and I subtract off Q2 transpose A3. And then I normalize that. Okay. I should mention, if I group these a little differently, if I have Q1 transpose or Q2 transpose, those are projection matrices. They're also outer products, but so what I'm doing here is I'm projecting A3 onto subspace spanned by Q1. Here I'm projecting on the subspace spanned by Q2. So really, this whole thing is A3 projected on the subspace spanned by these two, and I'm excluding it to make this resulting vector orthogonal to Q1 and Q2. Okay, so the general case is Rj is equal to Aj minus the sum from 1 to j minus 1 of qk transpose Aj, and then Qj is Rj divided by its norm. It's 2 norm. And that's it. That's the whole algorithm. And we do this for j equals 1 up to n. And you can verify, if you take a dot product of both sides of this, with any q less than j, you'll get 0. Everything will cancel out. Okay. Now I should mention, so
Dr. Landry?
yes.
Yeah, I think you are in a little bit of trouble.
You switch subscripts.
With my A's and my Q's.
When your K's and your J's are mixed.
R1 is equal to A1 at the very top.
Yeah.
So I thought the next one, is that Q1?
Yes.
Equals R, okay.
Okay.
You switched your
Okay. Yeah, I got it
J's
all.
and your K's too. You flipped them all.
So Q1, and then 8, that's okay, I'm working.
No, the K
And were your notes or reversed from that?
Oh.
Your J's and your K's are flipped.
Right. Okay.
Okay. Well, you have.
And then R3 is equal to A3,
Yes.
right? Minus Q1 transpose A3.
Yes.
Very good. Okay, thank you.
Okay.
On your sum, you have K equals 1 and then J minus 1 on the top. In your notes, you have just K. Or like, well, I mean, they're flipped, so you have.
Oh.
Yeah.
Okay.
So is that like a difference, or am I missing something?
Let's see. What you're looking at the notes is Graham-Schmidt specialized to this pre-love subspace case, which I haven't gotten to yet.
Oh. Okay.
All right. So you can hold up and follow along, but I will get to that momentarily.
Okay. All right.
All right. But yeah, I guess different subscripts.
Okay.
Well, I'll just trick around somebody. Better sort of the whole class or just you.
Huh?
I'll trick around somebody with my subscripts.
Oh.
The whole class or just you.
Oh.
Anyhow, now these dot products here, I'm going to name these R KJ, and these norms I'm going to call RJJ. And in this case, we make delta K is strictly less than J. So what we get as a result of this is A is equal to Q times R, where these dot products and these norms, those are the entries of capital R. So we start with the columns of A, we generate the columns of Q,